So what I want to show you next is how this is related to some fancier stuff, which, first of all, we don't know how to solve by hand, but second of all, these are examples that you work on in the lab. Newton's law of cooling. Okay. So you guys have already worked on this before, I think. So just a quick refresher. So when you've got an object of one temperature sitting in a room of a different temperature, it's described by the physical law, which you can put in words as saying the rate of change of the temperature of the object is proportional to the difference in temperatures. Well, why is that? So this makes sense because in the same room, a hot cup of tea will cool off faster than warm pizza. That should make sense. Okay. So as a differential equation in general, it looks like this. Now in this case, I've written it using, so when we do applied problems, I like to use what I call real variables. Now in math land, we get used to using x and y for everything. I think that's a terrible trap. Because, and you can see that when you get into an applied problem, I find it helpful to use real variables, letters where they stand for things and we know what we're talking about. So in this case, we've got the temperature of the object, I use capital T, and time, lowercase t, and k is just some constant. And then big T0 is your initial temperature. Okay. So, and in the lab, we actually had numbers for these things. Okay. So, Torricelli's law of draining. When you've got a cylindrical tank filled with water and it's draining, the height of the water y decreases at a rate proportional to the square root of that height. So as a differential equation, it looks like this. dy dt equals some constant k times the square root of y. And k is a constant just based on the actual size of the drain hole. So right now we're going to look at an example. So suppose that a drain has k equals 2, then your differential equation, well, you could figure out what it is. So when the water is 4 meters high, how fast is it draining? Sorry? Yeah, for what? Oh, yeah, I didn't say what the units were. But yeah, let's say meters per second, because I always use metric units. When the water is 2 meters high, 2 squared root of 2, so about 2.828 meters per second. So, and then, Steve, to go back to your question, in math class, you always say, oh, my answer is 2 radical 2, and I'm done. However, to say water is draining at 2 times the square root of 2 meters per second doesn't seem like it gives quite the right information. So I always like to say, well, what does that actually mean in terms of a magnitude? It's about 2.8. So that's why I do this. It just kind of makes sense to write it as a decimal approximation. Question? So what if you wanted to know in this situation how much water drains from t equals 0 to t equals 3 seconds? How would you do that problem? Or how would you start to try to do that problem? Yeah. So the integral. Okay. So let's just use k equals 2.
We use k as 2, sorry.
Do you what? What's your variable? Okay, is it dy or is it dt?
T, so we're
Okay, so someone defend why it's dy.
oh.
So y, yeah, I broke my own rule, right? Okay, so y is the height of the water. Maybe I should call it h. Hmm? Okay, y is changing, yes, but what's your variable?
T, because it's from 0 to 3, the time spent from.
Right. So we didn't finish writing this integral now. What's missing?
0 to 3.
From 0 to 3. Right? And Costa made the exact right point at the end there. From 0 to 3, what's going from 0 to 3? Time t. So t is your variable, and y, if you like, is your
So
function.
it's going to be y, the delta y is going to be equal to this?
Yes. And this is delta y, which you could think of as y evaluated at 3 minus y evaluated at 0. Okay. Now, of course, what do we do now? We have absolutely no idea. And as I said when I introduced this section, these are fancy examples which we don't know how to do by hand. So if you go on and take a differential equations class, you'll learn a little bit about how to solve problems like this. But we know a little bit about how to solve this, at least approximately. That was what we worked on in the lab. If you have a differential equation, you can actually do a calculation that approximates the answer. But to do it exactly, you need some fancy techniques that we're not going to learn in this class. Question?
Won't that just give you the meters if you integrate?
Exactly.
What do you mean by how much water? You want meters of water?
Ah, okay, because what is y measuring? The height of the water. So in other words, this would tell you that the water, say, goes from 3.5 meters to 2.2 meters. Therefore, it has changed the height has changed 1.3 meters in your tank.
And you have to find the volume.
You'd have to know something.
If you wanted to make this a problem about volume, you could make it a problem about volume, but that's not what it's about. Sorry?
I feel like there's a question that's what it's about. It says how much water, and I don't know what a meter of water is. I know what a volume of water is. Yeah, I know. But no, not volume. It's just the height. That's what I'm saying. He's saying it's just the height.
Change the question.
I have a question about.
Everybody else knew what I meant, but there you go.
Because I was thinking, like, the first thing I thought was you wouldn't take the integral, you would take the derivative, because that's the way I'm thinking of the units. I mean, you want to know the amount that changes per second.
I mean, you're exactly right. This is a problem about the height, so yes, I could be more specific. We're talking about the height.
So what would you get by doing the derivative?
Derivative of what?
Of the original function. That right now we're taking into
It depends what your original function is. What's your original function, an expression of?
Meters per second. What's it doing?
Okay, so that's a rate of change, how much the height is changing per second. So it's basically a velocity. If you could think of it of like there's like a top surface of the water, it's the velocity of the water. So if you take the derivative of that, what's the derivative of that? It's an acceleration, right? It would be how quickly the height of how quickly the speed of the change is changing, whatever, It's the acceleration. The rate of change of the rate of change. Yeah.
About the change in the cooling formula.
Okay.
Would that be considered as a second second level antiderivative because it's delta t equal k and again delta t again change. So if I write it out, it would be
No, and I'll tell you why. Because this would just be like t. This would just be like t minus 75. So it's just think of it as being like there's a constant in there.
okay.
Yeah. That's all I want to say right now. Okay. So let's see. How much do I want to say about this? All right. So I mentioned the fact that in your lab assignment, you already kind of looked at this stuff. There was an example about Torricelli's law of draining. There was an example about Newton's law of cooling. Another example was about basically where you had the differential equation which said y prime equals y. Okay. So here I've got a variation of that. I'm just going to talk about it briefly, and then I'll just say everything here is extra credit level material which you can look at your leisure. But I want to point out why something like this is really important, and also why it comes up often in the sciences. So think of this as like a social science example. Population growth. Let me clear this out. Okay. So typically you hear people say the population grew at 2% last year. What does that mean?
The rate of change.
Okay, so the rate of change is 2%. But 2% of what?
Total population.
2% of the current population. Which is quite irritating because the population is the thing that's our function. So in other words, what you're saying is that the rate of change, that should be, let me make that dy dt because we're getting used to using t at this point. Oh, I've got, yeah. dt's over there. So what we're saying is that the rate of change, dy dx, equals 2% is 0.02 of whatever the current population is, y. Now, of course, like I said, I like to use real variables. So go to the end over here. P is population, T is time. So dp dt equals 0.02 times P.
So it would be 0.02 of every subsequent increase in population.
Well, not of the increased population, but just the population itself. Right. So in other words, even just a very simple statement like this is actually something kind of complicated mathematically, if we try to think of it theoretically. Okay. And then the shorthand for this is if you just write P prime equals 0.02P. Okay. So that's very interesting. What do we do with that? There are several approaches. So I'll just start you. Suppose the population is 300 million, which is actually approximately true. What will it be next year? Right. Well, 2% of 300, so I'll just do it in millions. So 2.02 of 300 is 6. So next year, 306 million. Okay. So if we just write that as one equation, it would look like that. Well, mathematically, it's that. So think of the current year as t equals 0. Then f of 1 is just f of 0, which is 300 million, plus f prime of 0, which is the rate, which we know is 0.02p, times delta x, really delta t. And we said next year, so that's just a change of 1 year. Okay. What will the population be in 2 years? Right. So the lazy way to do this is to say, well, it's just going to go up another 2%, which is 6 million. But we know that's not right. it's more sensible to say, well, we know now that it's at 306 million, so I want it to grow by 2% of the 306 million. So you get 312.12 million people. But look at what we did. If you turn this back into the math that we know, here's what we did. We said we're going to start at 300 million, then it's going to grow by 2% of 300 million over 1 year. Then that's going to give me 306. Okay, well then it's going to grow by 2% of 306 million for 1 year. So what is this? This is an Euler approximation. Now, it's a hard Euler approximation because in order to get that 306, what did we have to do? You had to do the first step of the Euler approximation before you can do the second step of the Euler approximation. And the reason you have to do this is because you've got a very nasty differential equation. Okay. So anyway, so there's some more examples and work on this down there, but I wanted to give you an idea. First of all, this is obviously a very sort of wide-ranging type of situation that sort of makes sense that you might see all the time. And it turns out you do see it all the time. It turns out, as you may or may not have figured out from the lab, that this growth is actually, this differential equation is actually solved by an exponential function. So if you know some fancy math, you can actually prove that this is an exponential function. Right.
Like interest.
Like interest, exactly.
Compounding.
Right. So compounded either annually, in this case, or it could actually be, you could say compounded continuously, which will give you e to the something. Okay. Now, again, if you know fancy math that we've started to talk about, but it's outside the scope of this class, you can actually take the original differential equation, dp dt equals 0.02p, and you can actually solve it. You can use some techniques and actually solve it and get p equals, turns out equals e to the 0.02 t. So you can actually go ahead and solve, well, actually in this case it'd be 300 e to the 0.02 p. Anyway, that's beyond the scope of this class. But this is very important stuff. So for anyone who asks, what is all this stuff good for? Here's a good answer.